And welcome. Today we're going to talk about how to compute a Fourier transform of a Gaussian function. So what is a Gaussian function? Well, we'll define it as f of x is equal to e to the negative alpha x squared, where alpha is just a positive parameter. So it's just going to be a constant. Okay, so this function has a nice shape to it. It's sort of a bell curve. In fact, it is the bell curve. It's used commonly in probability and statistics. It shows up all over the place. And it looks like that. At 0, there's the peak to it, and it goes down like so. And one, really interesting fact is that there's no closed form antiderivative. For the Gaussian. And that means that any integral of the Gaussian is done numerically. We can't find an antiderivative, so we can't use the fundamental theorem of calculus. Of course, there is an antiderivative. I mean, this is a well-defined function. We can definitely take an area under this curve, and it's a well-defined thing from A to B or something like that. But we have to do it numerically in practice. There's no nice, easy antiderivative to write down for this function. We can't write it down simply, even though it does exist. So that's a nice fact about it. But it turns out this Gaussian function, because it's so useful and so important, we're gonna find out that Fourier transforms of Gaussian functions also have some nice properties, and so we're gonna go ahead and calculate it as another example of a Fourier transform. So let's write down what it is again. So this is our Fourier transform. 1 over 2 pi, integral from negative infinity to infinity of e to the negative alpha x squared e to the I omega x dx. All right, and we're going to combine our exponents as we would normally do, or as is useful to do. Plus I omega x dx. So we have this ugly integrand there, and we have this ugly exponent, but notice it looks like a polynomial in x. And so what we're going to do is complete the square. Okay, so how do we do that? What I'm going to do is I'm going to factor out that negative sign, make alpha x squared positive, and then put that negative sign there, omega x. And what we have to do always with completing the square is go plus c and then a minus c. And then we do it such that this thing can become a perfect square of the form a plus b squared minus c from there. Now I'm going to put that negative sign on the outside of the whole thing. So that means, so let's write this out. Let's FOIL this out. This is a squared plus 2ab plus b squared minus c. And that means that b squared is actually going to be c, all right? And 2ab is going to equal negative I omega x, right? And then a squared is going to be equal to alpha x squared. All right, so let's do a little switching around and changing around. And that means that b is equal to root c, okay? And then, and of course, our goal here is we need to find this c. All right, that's what we're trying to find, is this specific c, because we're going to find out that this form will be easier to compute our integral once we do a completion of the square. All right, that's the ultimate goal. All right, now we see clearly, we know alpha and we know what x is. It's our variable of integration. So a is easy to find, and that's simply a is equal to root alpha x, Okay, that looks good. And so all that's left is to find b. And b here can be found by taking this. We know what a is, so b is equal to negative I omega x divided by 2. And now we know what a is. We're going to divide by a, but a is root alpha over x. And the x's cancel there. And we're left with negative I omega over 2 alpha. Okay, and we said that b is equal to root c, so that means that if I square b, I get c. So, which is equal to, just put an equal there, it's going to be equal to negative omega squared all over 4 alpha squared. Sorry, no, there should be a root there, and that becomes regular alpha, not squared. Okay, that looks better. All right. So let's now put this together. So we'll put it back, and so what we have there is a negative on the outside, just like before. And then now, what is a again? We say that a. We said that a was root alpha x, and then b was negative I omega over 2 root alpha. We're going to quantity square that, and then minus from it right here. So c itself was a minus, so a minus and minus makes a plus. Omega squared all over 4 alpha. Okay, and we're going to put a parenthesis around that, and then we're going to take off the parenthesis. It becomes this root alpha x minus I omega over 2 root alpha quantity squared minus omega squared over 4 alpha. Okay, so it looks good. And now this is what I'm going to put in my exponent up here. And so that's what we're going to do, is put that in there. And that's going to help us solve this equation. So, so let's do that real quick. So now our Fourier transform from before is going to be equal to 1 over 2 pi integral from negative infinity to infinity, and then we're going to write down e to the negative, and then we're going to put that root alpha x minus I omega over 2 root alpha quantity squared, and then put a minus, and now I have to, I'm kind of, okay, it's a root, or it's going to be a square root, or it's going to be a square of omega over 4 alpha. I think I got that there. Looks good. Okay, good. All right, so there's my result, dx. All right, notice that this is an integral in dx, and this term here is, there's no x's in it at all. So 1 over 2 pi e to the negative omega squared all over 4 alpha. Integral negative infinity to infinity of e to the negative root alpha x minus I omega over 2 over root alpha times 2 quantity squared, and then this is dx. So what I see here is a very complicated expression, but the whole thing is sandwiched inside a square. All right, so what I'm going to do then is actually do a substitution. So I'll just do a u sub. So u is equal to root alpha times x minus I omega over root alpha 2. So du over root alpha is equal to dx. All right, so and then the limits of integration don't change, because when I take x going to positive and negative infinity, this whole thing also goes to infinity. And there's some details here going on because there's an imaginary part to this number. What exactly is happening there? But we're going to cover, just kind of gloss over that and just trust us that we can do such a thing. Because in reality, of course, this complex number is sitting in the complex plane. And when we're taking these limits from negative infinity to infinity, they're actually on a curve in the complex plane. But we'll gloss over those details and just charge forward. All right, and then so we're going to put this root alpha down there, integral negative infinity to infinity, e to the negative u squared du. All right, so this is the area under bell curve. All right. Now I said that this function, this Gaussian function, does not have an antiderivative, so we're going to have a hard time trying to figure out how to compute this integral. But it turns out there's a really clever way to do it. Okay, so let's write down our result again. I'm going to write it down here. So, oops. So, and it's going to equal, I'm going to put this over here actually. It was equal to 1 over 2 pi over root alpha e to the negative omega squared over 4 alpha. And that's going to be then that area under the curve of a different Gaussian function without the alpha. All right, so that looks nice. So what we want to do now is try to get a grasp on what this is. So I'm going to call that integral I. Du. Okay. Now a note, because this is a bell-shaped curve, it's symmetric. It's an even function, so it's symmetric about the 0 point. So I can actually just say it's 2 times just the integral on the one side. Okay, that looks good. And now what I'm going to do is I'm going to square the whole thing. So I'm going to say I squared is actually equal to 4 integral 0 to infinity of e to the negative u squared du. But then what I'm going to do is rather than wrap this in a square term, I'm going to do is I'm going to have another integral with another variable of integration, which I'm going to call, we'll just call it y squared dy, right? That's just 2 copies of this integral squared, so that makes it squared, right? All right, so notice that this is a different variable of integration to that, and that makes sense. That those are just shorthand variables. So that means I squared is equal to 4. But what I'm going to do then, because anytime you see a product of 2 integrals of different variables, you can always bring them together, like such. E to the negative u squared plus y squared. We'll put that in a all quantity, du dy. So this looks like an area integral. Okay, that's an area integral. Looks pretty good. And so what this is then is, where is this area? What is the region? So if I want to write this down, I'm going to write it down as a, and our function there is now going to be u squared plus y squared, quantity, dA. And so I'll call this D, actually, this region D that I want to integrate over. And it's literally just the first quadrant. So we'll call this the u variable. I'm going to call that the y variable. And D is just that whole first quadrant, out to infinity in both directions. Okay, so it's a standard area integral that all of you 3140 students know how to compute. So I'm going to use polar. Polar coordinates. So again, r squared is going to be equal to u squared plus y squared, and u is going to be equal to r cosine theta, and y is going to be equal to r sine theta. Okay, looks good there. So of course then that du dy is going to equal r dr d theta, and then d in the polar coordinate system is going to be r is in the interval 0 all the way to infinity, and then theta is in the interval 0 all the way to pi over 2, right? Because we're going from here all the way up and stopping at pi over 2. Okay, looks good. So now I'm going to put all of this together, put that down there, and that becomes 0 pi over 2. Integral from 0 to infinity, and then we have a e to the negative r squared, and then we have an r dr d theta. I'm going to do that theta integral first, actually, and that's we have to remember we have that 4 there, and we have that 4 there, and that's just coming from, that's just tagging along in our problem. At any rate, we have a 4, and then we integrate the theta, which is really simple. It's just going to be pi over 2, integral 0 to infinity of r e to the negative r squared dr. Okay, looks pretty good. So that 2 cancels. We're just left with a 2 there. Then finally what I see is that we see a derivative relationship here. And we can actually calculate what the antiderivative of this integrand is. And now it's going to be, I'm going to say this is w is equal to r squared. So dw over 2r is equal to dr. And so then we are left with pi sitting there because we're going to cancel yet another factor of 2. And we're left with 0 to infinity of e to the negative w dw. And that, of course, is just going to be pi. All right, so that's the result. So let's put this all together then. So if I write this down then, so this whole integral here, now that was actually I squared. So what is I then? I is going to be root pi. All right, so now you have a way to calculate, even though we didn't have an antiderivative, we just used some kind of clever trickery, we're able to find out what the integral of the area under the Gaussian curve on the real line is, using some clever tricks. So let's now, let's just write all this down. So I can actually write it down right here, and this remainder of space. I'll just rewrite it here. So that's going to be root pi, and we can put this all together then. So we have here Fourier transform of the Gaussian function is going to be it's going to be 1 over root 4 pi alpha, and that's just doing a little algebra arithmetic, e to the negative omega squared over 4 alpha. Okay, what's neat about this, and that's of course going to be the Fourier transform, the capital F of omega. This is a, so this is a Gaussian in the Gaussian family, and that's going across using the Fourier transform. And this is also a Gaussian. So in fact, this is this unique family of functions where the Fourier transform of a Gaussian function is also a Gaussian. And so that's really neat. And now we can also go back, right? So that means that any Gaussian function that I have over in the frequency domain, omega, if I map it back using an inverse Fourier transform, I also get a Gaussian. All right, so, and now just for notational purposes, I want to actually write this down. I want to write this. What if I have a Gaussian in the frequency domain? I'm going to call it e to the negative beta omega squared. If I want to go back, I can just do the arithmetic or the algebra to find out what it has to be, but I'll just write it down here. The inverse Fourier transform will be root pi over beta e to the negative x squared over 4 beta. So we'll just put a square around that whole thing. So that's what it is. All right, so now we have a really neat result. And we're going to use this over and over again later on. So we have to be very good about using Gaussians. And that's why I wanted to go over this example. Thank you very much.